Welcome to the module, Building a Motion Model and Post-Processing. In this module, you will learn about different types of mates, how to add local mates to the assembly, and how to create an absolute as well as a relative values results plot. This module is split into two parts. In Part 1, you will learn how to build proper SolidWorks motion models for kinematic simulation and create local mates for a SolidWorks motion study. In Part 2, you will learn how to use the function builder to construct functional expressions for motors and forces. You will also learn how to create and modify kinematic plots. Along with that, you will learn how to create an absolute as well as a relative values results plot with respect to a local or global coordinate system. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. The crank slider model is used in a variety of engineering applications, such as a steam engine or the cylinder of an internal combustion engine. In this module, you will set up the mechanism for the crank slider model. You will use SolidWorks mates that most closely represent real mechanical connections. The crank is driven at a constant angular velocity of 60 RPM. Based on this, we will determine the torque required to rotate the crank part. Mates are nothing but constraints. Mates can be classified into two main groups. 1. Mates used to constrain the relative motion of a pair of rigid bodies by physically connecting them. Examples are hinge, screw, cam, etc. 2. Mates used to enforce standard geometric constraints. Examples are distance, angle, parallel, etc. Click the arrowheads along each edge of the content frame to move to the next slide. The concentric mate aligns both the bodies to common center. It allows both relative rotation as well as relative translation of one rigid body with respect to another rigid body. The concentric mate origin can be located anywhere along the axis about which the rigid bodies can rotate or slide with respect to each other. An example is a piston sliding and rotating inside a cylinder. A hinge mate is essentially a concentric mate with restricted translation between the two components. In SolidWorks Motion, the hinge mate is used instead of a combination of concentric and coincident because the mechanical joint is a hinge. Hinge mates are found in the Mechanical Mates tab of the Mate Property Manager. Point-to-point coincident mate permits free rotation on a common point of one rigid body with respect to another rigid body. The origin location of this mate determines the point at which the rigid bodies can pivot freely with respect to each other. An example is a ball and socket joint. The lock mate locks two rigid bodies together so they may not move with respect to each other. For a lock mate, the origin location and orientation does not affect the outcome of the simulation. A real-world example of a lock mate is a weld that holds two parts together. The two face-to-face coincident mates allow one rigid body to translate along a vector with respect to a second rigid body. The rigid bodies having this type of mate cannot rotate with respect to each other. The location of the origin of a translational joint with respect to its rigid bodies does not affect the motion of the two bodies, but does affect the reaction or the bearing loads. A universal mate permits the transfer of rotation from one rigid body to another rigid body. This mate is particularly useful to transfer rotational motion around corners or to transfer rotational motion between two connected shafts that are permitted to bend at the connection point. The origin location of the universal mate represents the connection point of the two rigid bodies. The two shaft axes identify the center lines of the two rigid bodies connected by the universal joint. Note that SolidWorks Motion uses rotational axes parallel to the rotational axes you identify, which pass through the origin of the universal mate. The screw mate constrains one rigid body to rotate as it translates with respect to another rigid body. When defining a screw mate, you can define the pitch. The pitch is the amount of relative translational displacement between the rigid bodies for each full rotation of the first rigid body. The displacement of the first rigid body relative to the second rigid body is a function of the rotation of the first rigid body about the axis of rotation. Point-on-axis coincident mate permits one translational and three rotational motions of one part with respect to another. A parallel mate permits only translational motion of one part with respect to another. No rotation is allowed. In the image, the blue X part can move relative to the ground in the X direction. The red Y part can move relative to the X part in the Y direction. The Z part can move relative to the Y part in the Z direction. Finally, the red, yellow, blue cube on the Z part has a curvilinear motion relative to the ground but always stays parallel. The perpendicular mate allows both translational and rotational motion of one part with respect to another. It imposes a single rotational constraint on the components so that the component axes remain perpendicular. If there are no mates in the SolidWorks assembly, or if we wish to define the connections differently than the SolidWorks mates, we can add local mates directly to the motion study. Local mates only apply to the study to which they were added. To add local mates to a motion study, make a motion study active and add the mates. Mates created in SolidWorks can be transferred to the motion analysis and used as mechanical joints. Note that with a motion study active, any mate added is only applied in that motion study. Let us see how to add a local hinge mate. Click Show Me to launch a demonstration video. The 3D crank slider assembly file has been opened. SolidWorks Motion assumes that all components that are fixed in SolidWorks should also be fixed in SolidWorks Motion, so will have no movement. Furthermore, all components that are floating are assumed to move, but their movement can be constrained by mates. Currently, no mates exist in this assembly, but 3 parts are fixed. Fixed components are designated by the letter F in front of the part in the command manager. The fixed parts include the collar shaft, arm mount, and crank housing. The remaining parts will need mates to constrain their motion to that expected of the mechanical system. Verify that the document units are set to millimeters, grams, seconds. Right-click the Motion Study 1 tab and click Create New Motion Study. Make sure that Motion Analysis is selected as the type of study in the Motion Manager. We will need to move the components that are not fixed to separate the assembly. We are doing this only to make it easier to select faces and to keep track of what components are mated. Click Mate. Pin the Mate Property Manager. Click Hinge from the Mechanical Mates section. For concentric selections, click the cylindrical face of the shaft, and then click the cylindrical face of the hole. For coincident selections, click the end face of the shaft and crank housing. A warning pops up because the timeline is active and the mate changes the position of the crank at the starting position of the animation. Click Yes. Click OK twice to close the Mate Property Manager. Scroll down to the Mates section in the SolidWorks Motion Manager tree. Expand Mates. Notice that this mate is only located in the Motion Manager and not in the SolidWorks Feature Manager design tree. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about adding a local hinge mate. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Let us see how to add other local mates. Click Show Me to launch a demonstration video. Click Mate. Click Concentric. Add a concentric mate between the spherical surfaces of the parts Link 1 and Crank. To do this, click the spherical surface of Link 1. And then click the spherical surface of the crank. Click Yes to the warning pop-up window. Click OK. Click Hinge from the Mechanical Mates section. For concentric selections, click the shaft of the arm mount and then click the hole of the arm. For coincident selections, click the front faces of the arm mount and then the arm. Click Yes to the warning pop-up window. Click OK. Now that we have already seen how to create hinge mates, we will create hinge mates between Link 1 and Cardan, Cardan and Arm, and Link 2 and Arm. A hinge mate has been created between Link 1 and Cardan, Cardan and Arm, and Link 2 and Arm. Similarly, we will add a concentric mate between collar shaft and collar, and the other end of Link 2 and the pin on the collar. A concentric mate has been created between collar shaft and collar, and the other end of Link 2 and the pin on the collar. It's recommended that we rotate the crank to make sure that all the components are moving as expected. We can see that all the mates have been added in the Motion Manager tree and not in the Feature Manager design tree. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about adding other local mates. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed the simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module Building a Motion Model and Post-Processing Part 1. Here are the key takeaways from the module.